Okay, so here we have barium chromate. And like I mentioned, the solubility now is given to us in grams per liter. So when we set up our KSP, so barium chromate would be, we have +2 and -2. So our KSP is going to simply be, right, a 1-to-1 ratio here. So it's just going to be chromate and barium. Okay, but we do need to determine the concentration of our X in moles per liter, right? So we have 2.8 times 10 to the -3, right, grams per liter. So really you want to get rid of the grams and convert it into moles. So we're going to do that by multiplying, or actually should say dividing by the molar mass. So the molar mass, of course, just to quickly recap, I know we've done this before, but you would take your barium, chromium, and then 4 oxygens, add the atomic masses for all of these together. So in 1 mole, we have 253.37 grams. And remember, I always tend to do 2 decimal points for molar mass. So that's going to end up giving us moles per liter, which is exactly what we want. So I'm not going to round here, but this is our concentration in moles per liter, which would be equal to our X, which, because it's a 1-to-1 ratio, we would pop in as our 2 concentrations. So our KSP value here, let me just double check on this, so it'll be 1.105 times 10 to the -5 squared. So we're going to get 1.22, and we're going to do 2 sig fig, so 1.2 times 10 to the -10 in this case. All right. So here we have another example of something where it is in grams per liter. So same exact thing. So this is for silver oxalate. So again, at any point in time, pause the video, give it a try, and then come on back to us. So our KSP expression is going to be silver squared, and then of course we have our oxalate. So of course we would have to convert this into moles per liter. So the molar mass here is, actually I didn't even jot this down. So we would have to add this up. So we have 2 silver, we have 2 carbons, so the 2 carbons, 12.01 times 2, plus 4 times 16, and then we would have to, let me just grab silver's molar mass per second. Okay, so silver is 107.87 times 2, so we get a molar mass here of 303.76. So we end up having a value here, 0.033 of just make sure we have the right thing, 0.86, pardon me, times 10 to the -4 moles per liter. Now, same as before we plug in, so this would be equal to our oxalate, but before we plug this into our silver, we would have to make sure that we are doubling it. So once you do that, your KSP value we end up with is 5.1 times 10 to the -12 as our final answer. Okay, next question. So student prepares a saturated solution by dissolving 5.5 times 10 to the -5 moles of magnesium hydroxide in 500 milliliters of solution. Calculate the KSP. So our KSP value, of course, we know is going to be our magnesium and then our hydroxide squared, right? Now, the only difference here, of course, compared to any of the other ones, is that we have to calculate the concentration, which is moles per liter, right? So keeping in mind, of course, we have to convert milliliters into liters. So we have 5.5 times 10 to the -5 moles in 500 milliliters. And of course, we know that 1,000 milliliters is equal to 1 liter, right? So we get here a concentration of approximately 1.1 times 10 to the negative 4 moles per liter. And then, of course, we're going to plug this into our magnesium because this is now equal to our X. But we have to remember to double it when we put into our OH. So our KSP value here is 5.3 times 10 to the negative 12 at that point. All right, so now we have a student evaporated 150 milliliters of a saturated solution of, this is magnesium oxalate. If 0.16 grams of solute remains, calculate the KSP. Okay, so we have the volume, we have the gram value. Okay, so essentially they're telling us that, let's just jot this down. So our mass that we have is 0.16 grams. So in this case, we would have to determine the number of moles here. This is the amount of this, of course, original mole value we can determine. We can determine the concentration and then figure out the KSP. So our KSP expression, we might as well write this down. Magnesium, and then we have our oxalate, -2. Okay, so we're going to determine our concentration. So let's take a look. We'll do moles first. 0.16 grams divided by, or we can do this, 1 mole. And then we have our, I feel like we just found this, but it was for silver oxalate. So let's take a look for magnesium oxalate, the molar mass. Okay, so the molar mass here is 112.32 grams. So that's going to give us our mole value. So we have 0.16 divided by 0.16 divided by 112.32. So we have a mole value of 1.4245 times 10 to the negative 3. And we might as well determine concentration at this point into 150 mils, which we know to convert into liters. Okay, so we get here a concentration of, just make sure we're on the right track here, 9.5 or 497, that's close enough, moles per liter. And that is now essentially our X. It's a 1-to-1 ratio. So we're going to take that value and square it. And we get a KSP value of 9.02. We want 2 sig figs, so actually it's just going to be 9.0 times 10 to the negative 5. Okay, so it's just like all different variations of essentially the same thing, right? Determining the concentration one way or another, making sure that you have your ion ratios that are being taken into consideration into our KSP expression. All right, so this is just a table that's actually it's in your book. It's on page 245 in your work text. But it's a table that has a whole big list of what the KSP values would be for some ionic compounds at, of course, a standard ambient temperature of 25 degrees. So you may have to refer to these, of course. This is not an all-inclusive list. There are a ton of known concentrations, as it should say, saturated solution KSP values at this temperature. So just to give you an example of like variation here. So of course, remember we mentioned the larger the KSP value, the higher the solubility. So all of these values are actually pretty low in terms of solubility. Some are very low. So copper 2 sulfide, I would say, has an incredibly low solubility especially compared to something like calcium sulfate, right? So the higher the value, right, the larger the value is, the more soluble, the more ions that happen to be in that solution. So we're going to make reference to some of these in our upcoming examples. So now we have a case where we are going to be asked to determine the solubility. So remember, anytime it's asking us to determine the solubility, that is the same thing as determine the concentration of the solute in your saturated solution, right? So we are looking at silver chloride and we want to express that in moles per liter. Okay, so silver chloride, here is our solubility equilibrium. So the KSP expression is going to be silver and chlorine. So we have this KSP value. We can look up this value from our data table. Okay. These values here, we do not know what they are. So we're actually just going to use X as our variable, right? So remember, it's a 1-to-1 ratio. So really it's 1X and 1X. So when we determine this here from the table, or when we look it up, I should say, silver chloride, let's go back for a second. Actually, I don't think I put the whole chart here. But anyways, it's in your table, I promise, in your textbook. Silver chloride is 1.8 times 10 to the negative 10, which is equal to essentially X squared. And then we are going to take the square root of both sides to determine X. So X is 1.34 times 10 to the negative 5 moles per liter. So remember, that is equal to X, which is also equal to our silver and our chlorine concentrations, right? So anytime it's asking to determine the solubility of something, essentially it's almost like they're saying determine what X is. All right, so same thing is happening here, right? We have iron to sulfide. The difference here is we want to convert it into grams per milliliter after the fact. So iron to sulfide, it looks like this. So our KSP is going to essentially be iron ions and sulfide ions. Again, a 1-to-1 ratio. KSP, if we look this up in your chart, is 6.0 times 10 to the negative 19. And this is just 1-to-1 ratio, so it's just X squared. So this will give us 7.746 times 10 to the negative 10. But remember, this is in moles per liter. So we need to convert this. So first of all, let's convert our liter into milliliters, which is what they are asking us to do. Right, so our liters are gone. And then we will also need to use our molar mass again. Of course, because we want to get rid of moles and we want values of grams. So we want our moles to be on the bottom and our mass on top. So the molar mass of iron to sulfide is 87.91 grams per mole. So what ends up happening is we're going to end up getting, at the end of this, our grams per milliliter quantity. So keep in mind, again, there's no like significant digits to refer to here. So I just left it as 6.81 if you did 6.8, or I guess if you left it at 7, but I would always say more is better than less. But I would not ding you on sig figs in that case. Okay, and then of course we remember capital M is the same thing as moles per liter, right? So here we have lead 2 iodate, and we are determining the concentration here once again. And I may have to continue this into our next part. Our next part won't be as long. We really just have a few more examples to go through. The actual content that's to be covered in this section has already been done. We're just going to continue with the rest of our practice problems.